Dr. Gotzi and Dr. Oyama to chair this session, please.
So firstly, I would like to introduce first paper is radiation-less cold fusion by small crystals or better N-cell requirement and energy transfer to the lattice by Dr. Chan. Please. So 15 minutes presentation and 5-minute discussion.
Okay, that's the title of my talk, which has just been read. What I'm going to do is go over, explain again the ion band state theory, and address these questions of small crystals and the N-cell requirement. And as you know, we approach the problem of nuclear reaction in terms of bound state systems where you don't involve particles moving in cross sections. You have two-particle wave functions that are involved. And this ion band state theory addresses questions, experimental problems like why does fusion take place in a deuterated solid? Why do you get helium-4? Why is there no radiation? Why do you get this in deuterated metals and not in deuterated molecules? And why, as Radha-Manzan's work indicates, do you get more heat out of small crystals under the same chemical conditions, chemical potential kind of conditions? And as I say, this is the ion band state theory. We're talking about block functions, functions which have equal amplitude distribution in each unit cell. And we illustrate what is basically, we believe to be a three-dimensional block function problem by two-dimensional calculations that have been made by Pushka and Niemann to show you the variety of the types of states that are possible as block states in metal hydrides, metal deuterides. These calculations are for metal hydrides. This is the distribution for the ground state on a nickel 100 surface. This is the distribution on nickel 110 surface, and this is the distribution on nickel 111. Now these states have, although these are all block states, they have a different character. These two states we can consider as being indirectly accessible states, and this as a directly accessible states. And that's a concept that is based upon the following thinking. If you deposit electrolytically a single deuterium or hydrogen ion, in this case proton, on the surface of this state, it will not spread out in time. It cannot override the potential saddle points to go over to another unit cell. It may get thermally activated and jump over or occasionally tunnel through, but it always appears as a localized interstitial. In this case, if you put a particle localized, the wave function will spread out in time in the direction where it flows over easily over the barrier between adjacent unit cells, but it can't adjust from this line to cover this line. In this case, it can spread out in 2 dimensions, and after a long period of time, it may resemble the fully symmetric distribution, spatially symmetric distribution, where every unit cell is equivalent in the ideal situation. So you see no difference in this curve that's plotted with this. Now we use these block function pictures to also, again, illustrate the fundamental differences in how matter, quantized matter, behaves in a solid. If we have this particle on the 100 surface, as I say, it stays localized. That is basically chemistry. Interstitial localized wave functions. In this case, it is basically spread out. This particle, so quantized matter is sometimes mostly particle-like, in this case, with some matter field properties. It's not a point, it is spread, its wave function is spread out. These wave functions are basically the ion equivalent of electron orbitals around atoms. These are the density distributions of ions on the surface. Isn't the story? Okay. This distribution, the point is this distribution is a distribution for a single ion. The amplitude of this wave function is very low everywhere, but it's equal in each unit cell. Now, if you put two ions in the chemical case, then you have two localized distributions, which may be side by side or far apart. That's the situation when you have two particles which are acting as in chemistry. But if you do put two particles in this distribution, then both of them spread out, and if they don't repel each other too strongly, their distributions in space are basically identical for the two-particle system as compared to the one-particle system. And you describe this kind of a distribution by a two-particle wave function. Now, the ion band state theory really depends on a number of assumptions, and these three assumptions are particularly important for what we'll be talking about. The paired band state deuterons are described by a 6 degree of freedom two-ion block function in center of mass separation coordinates. That's assumption that we really make in this theory. And this block condition is assumed to apply to both factors in the two-particle wave function. And another assumption that we make in the theory that's required for explaining fusion is that you have a quantum mechanics superposition principle which applies to the two-particle stationary state description of the system. But this stationary state, which is the best view of reality, can be expressed as a complete sum over a complete set of states, Liouvanier states, which treat the particles as whole integers in assignable unit cells. And the other principle that we have to use to explain fusion is that in the stationary state description, you have electron neutrality in every unit cell. You have electrons that basically screen the field from one unit cell to another, and that's an essential aspect of the theory. So the theory really will only work for metals or maybe semiconductors, but not for insulators. Now, how do you describe this kind of a two-particle system? If you have no basic repulsion interaction between the two ions in the two-particle wave function, you set it up in terms of single particle wave functions, a product of one describing particle 1, one describing particle 2, but you have to include the exchange principle. And since we're dealing with a periodic solid, each of these wave functions has to be a block function, which meets this requirement that if you add to a position a lattice vector, you get the same amplitude in another part of the crystal. But the point is, these are independent block functions, so you can add independent lattice vectors. But if you turn on the repulsion interaction, you introduce an additional term in the potential function, and you really have to describe the system not only in terms of its position in real space, but also a factor that tells you what happens when the particles formally, you might say, or their lattice equivalent, get close together or on top of each other. Now, as I say, we make the key assumption that both of these psi function and g function are both block functions. The key thing is that this pictures. Well, all these two-particle pictures are 6 degree of freedom problems. Basically, you might call them 6-dimensional descriptions of the system. Now, how do you visualize that? Well, to really visualize that, you need to have 2 3-dimensional pictures and to show an amplitude versus each of the 3 dimensions involved in the pictures, totaling 6 dimensions. Well, to simplify the problem for me, I've taken a line through the lattice that goes through saddle points in the crystal, and plotted here the amplitude of the wave function versus its position along the line. And at the saddle points, the wave function has low amplitude, and it's higher in the center of the potential wells, which are what really bind the ions of the crystal. Now, when you have a nuclear reaction, this function is defined in true physical space within the crystal. And when you have a nuclear reaction, it occurs everywhere in this real space. It's a coherent process, completely covering the crystal. Now, in our assumption, following our assumption, in separation space, which is where you see the effects of the Coulomb repulsion, that is also a block function by our assumption. And at the R12 equals 0 point, you have the singularity in the potential function, which is canceled by a singularity in the slope of the momentum factor in the wave function. And that cancellation occurs at a point which is the cusp point. And this cusp, because of the block function assumption for this factor, is present throughout in each unit cell of separation space. So you think, as far as the reaction goes, is viewed in separation space, it occurs at the cusp points, at all n-cell cusp points in separation space. So you have to get this 6-dimensional picture to really understand. Oh, well, let's see, I want to go back one other factor on this. We talked in ICCF-6 of how the crystal size affects the amplitude of these cusps. When the amplitude of the cusp is determined by what cusp depth minimizes the energy of the system. If the crystal is large, the cusps become vanishingly small, and the whole system collapses to something that can be really represented by just 3 dimensions in real space. At each of these dimensions, you have a charge density describing the electrostatic behavior of the system. But when you have a smaller crystal, down around 10 to the 4th unit cells, then as you get smaller, the cusps grow and eventually get to 0, at which point you have no overlap between these spread out deuterons, and you have no possibility of nuclear reaction. And as you approach that point, actually this block function description of the system no longer becomes valid, and some other description, such as a molecule, then becomes an appropriate way of viewing the system. So I'm not going over that energy minimization calculation during this talk because of time limitations. I want to go over and talk about why small crystals are better. The essence of the argument of why small crystals are better is that it turns out that the number of fusions per second that you calculate, say for a crystal, depends only on the concentration of the band state deuterons, and it occurs as a square of this concentration, as you would expect with a two-body reaction. Now, how do I get this point? Well, this is basically not a collision, is a self-interaction of a quantized matter field. And it depends, the reaction rate calculated by the Fermi-Golden rule depends on the strength of the matter field that's present in each unit cell. And the matter field concentration is really measured by the amplitude squared of the deuterons normalized to the unit cell size. And since it's a two-particle reaction, this normalized wave function has each deuteron introduces a factor of 1 over n cell in this double deuteron field. But in quantum mechanics, you have microscopic reversibility in reaction rate calculation, and you have equally the other factor that enters in the concentration or field strength factor is the field strength of the product. Well, the product is 1 helium per crystal. So the field strength there is 1 over n cell. Okay, so if you look at the reactivity of a single unit cell, you have this 1 over n cell factor from the deuterons and 1 over n cell from the helium. But we're dealing really with a many-body wave function. And how many pairs do you have if this many-body wave function has n sub d deuterons in the crystal? Well, this is the exact calculation for the number of pairs, basically np squared, and that really is equivalent to this. This factor cancels that factor, and so this is the reaction rate per unit cell in that crystal. And if you add up the unit cells to get the reaction rate in the crystal, you just get another factor of n cell, and you get this result. So if you have equal reaction number of fusions per crystal, regardless of the crystal size, the more crystals you can get per cc, the better, as long as you don't get them so small that they interfere with overlap. So that's basically why small crystals should give you a higher power density than larger crystals. And the other factor that I want to talk about, the other factor I want to talk about is the de-excitation of the nuclear state. We've been talking about the electrostatic part of the wave function, but it also has a nuclear part. And how does the nuclear part, or the nuclear changes that are made possible because of electrostatic overlap of the electrostatic system, how does that ever do anything with a lattice? Well, the point is, once you get the overlap, you have the possibility of condensing something of atomic dimensions into something of nuclear dimensions, and you basically have a reversible fluctuation until energy is transferred from that nuclear system. But when you change deuterons to helium, you change the quantum of mass from mass 2 charge 1 to mass 4 charge 2. And when you change that quantum of mass as a purely quantum mechanical effect, you change the distribution of charge in the boundary region of the crystal. At the edge of the ordered, when you get out of the ordered domain of the crystal, the wave function of deuterium falls off more slowly than the wave function of the helium. And so as a result, you have a fluctuating charge density distribution at the boundary, and that charge distribution scatters, inelastically scatters, the band state electrons that are providing electrical neutrality in each unit cell of the system. And once energy is transferred to these band state electrons, then just from conservation of energy, you can never go back to the spread out deuteron state. And so the reaction goes to completion, presumably in the boundary region, mainly by this electron scattering process. But there are also some photon generation that go on with the fact that the product lattice itself is slightly shrunk compared to what it was before the reaction. So that's basically all I wanted to say. As some people have pointed out, a lot of the problem in this picture is how you prepare the system in a block state. And one way you can do it is if you have a ground state chemical situation like this, the excited states of this system are almost certainly all block states. There's an article by Cosello who treats protons in neodymium, and the excited states are block states. Well, a block state will overlap a state like this, but to go from that state, which is pretty much spread out, to a state which is very strictly requires the equivalence of every unit cell, which is truly a very well-defined block state, you have a transition that, which is presumably exothermic, and you end up in a state like this. Well, this state cannot easily decay in this state. In fact, the energy level of the state could be very similar to this state. And we think that this inability to go from this state to this state could be the major cause of the heat after death phenomenon, which is seen by Weissman and Pons. So that provides the means of it preparing the state, and it seems to fit the experimental situation.
Thank you. Time is over, so but Pekka, we are asking you a couple of questions, if you have. Please.
When you say small crystal, do you necessarily mean a crystal which is bounded by a gas or a vacuum, or do you also mean a grain within an assembly of grains in a metal?
I mean an ordered domain in a conducting solid. The typical thing might be an embedded crystal. And these band state electrons can extend beyond the volume of this embedded domain. So the heat is can be given off in a larger volume than the actual volume of the embedded ordered domain.
At finite temperature, you start to generate phonons in areas of disorder. So you can form domains within a larger crystal as well.
So a small crystal bounded by grain boundaries is not as good as a freestanding crystal bounded by vacuum?
Probably better, because the electrons that are being scattered extend over a larger volume.
Well, potentially you could even have a coherent effect involving one crystal with another that's separated through an interface.
Okay, thank you again.
The next contribution comes from Osaka University and is entitled Measurements of Excess Heat and Nuclear Products in PD D2O system using twin open type electrolysis cells. The paper is by Fukuoka, Ikegama, Takashi. The paper is presented by Dr. Fukuoka.
Thank you, Jim. We have been investigating cold fusion phenomena during heavy water electrolysis. We already reported slight excess heat with big neutron emission in energy of over 3 MeV at ICCF-6. The aim of this study is to reproduce abstract results and to perform more reliable measurements to cite the correlation between excess heat and neutron products. At this time, I will talk about improvement of X-ray for colder fusion study at the first. And next, I will explain the experimental and results. Finally, I will mention the conclusion. If nuclear reaction takes place in solid, high energy charged particle emissions, neutron emissions, and excess heat are usually expected. In that sense, the charged particle is difficult to detect because of attenuation in solid, water, and so on. But emissions of characteristic X-rays and brain-strong X-rays will be caused by slowing down of the charged particle in material. Since Most of these emissions will be characteristic X-rays. Child battery can be detected indirectly by the detection of characteristic X-rays. Paradigm has been used as a cathode of heavy water electrolysis in our group. Because characteristic X-rays of paradigm K alpha and K beta are from 21 to 23 keV, it is necessary to measure the X-rays of this energy range. A cadmium telluride solid-state detector was chosen to detect these X-rays because of its high energy, high efficiency in energy less than 90 keV and its compatibility to be used at room temperature. But cadmium telluride detector picks up electromagnetic noise or mechanical noise easily at long-term measurement, and it will give a bad influence upon the accurate measurement. So, we introduced for X-ray measurement two-dimensional pulse shape and pulse height analysis to reject noise signals. This is the principle of right-time analysis. Most of noise signals are telephone genuine signals by its right time. The right time is defined as the time which takes the linear amplifier output pulse to rise from 20% to 80%. This is X-ray two-dimensional spectrum of emission. It is plotted for lifetime of pulse at the axis of the scissor and pulse height on the vertical line. We can recognize the lifetime of X-ray signals to be about 2 microseconds and to put between the line AB and the line CD. This is two-dimensional spectrum of long-time background X-rays. The signals of which lifetime were about 2 microseconds were accepted as X-ray signals, and the signal less than 1 microsecond were rejected as no signals. This is background spectrum before lifetime discrimination and background spectrum after lifetime discrimination. This lifetime discrimination can reject most of noise signals. Now I will explain the experimental. The twin open type cells and measurement system were designed as this diagram. The electrochemical cells and measurement system were twin type. In order to perform two-type experiments at the same time, for example, heavy water electrolysis and light water electrolysis using paradigm cathode for both cells. The advantage of this twin experimental system is that simultaneous events happening in both cells could be rejected as the noises. Using this system, the accurate comparative experiments of cold fusion can be performed. The system includes two open-type electrolysis cells called F cell and B cell. Two X-ray spectroscopy systems using cadmium telluride detectors and two fast neutron spectroscopy systems with NE213 detectors. One power supply is connected to cells in series and supplies the same electric current. Current flow was connected to cells also in series. This is the structure of open type cell. The first cathode, 25 times 25 square millimeter and 1 millimeter in thickness, is followed by thermal electrode folder, which follows the anode wire. Current flow in the coolant pipe and temperature potential distribution of the electrolyte is kept uniform by star. The effluent gas, which is generated by electrolysis, goes out through the gas outlet. The electrolyte temperature was measured by chromosomal sample. The output part of electrolysis is linear function of the sample output, and the coefficients of the linear function were determined by the calculation using nickel cathode in every experiment. The excess energy was determined by the difference between output power and input power to the electrolyte. The distribution of the deviation from calibration line at the calibration line is like Gaussian distribution, and statistical error is estimated by 3 times of standard deviation. This is the X-ray measurement system. The cadmium telluride detector, 2 times 2 square millimeter, was placed in front of the cell. Using this system, noise component in cadmium telluride signal was distinguished by the light time and separated from real X-ray signals. The measurement range of the system was about from 6 to 19 keV in energy. The detection efficiency of K-alpha and K-beta X-rays was 0.076%. X-ray events are counted every 4 minutes besides spectroscopy. The Ikegama pulse separation technique is applied to neutron measurement using an Ne213 fast neutron spectrometer, which was placed in front of the cell, as shown in this diagram. The gamma ray component and noise component could be separated completely by this diagram. The measurement range of neutron is from 0 to 9 MeV in energy, but one of the Ne213 detectors did not perform light measurement in low energy less than 3 MeV because of containment alpha particle emitters, which included in this Ne213 detector. So it was used exclusively for high energy. Neutron events were also counted every 4 minutes in addition to spectroscopy. At the most of experiments, the electrolysis current density was changed periodically from low to high for the readers in every 3 or 6 hours, called low-high mode, in order to give dynamic change of nuclear accumulation in palladium metal. But for week at the beginning of electrolysis, the electrolysis current density was kept to be 160 milliampere per square centimeter, constantly called constant mode, in order to keep palladium cathode from cracking, except for rounds from 1 to 3. The electrolyte was 0.2 mole within OD heavy water solution. Palladium cathode used in experiments were pre-processed by various treatments, for example, cold baths, anneals, and so on. This is a summary of the experiment. In the table, yes means that anomalous events were observed. There are no excess heat, 4 cases of X-ray emissions, and 1 case of neutron emission. This is a typical data of heat balance when the electric current was kept 160 milliampere per square centimeter for the top figure, and when the current density was changed from 160 to 6040 milliampere per square centimeter for the reverse inside for bottom figure. The excess power during thermal equilibrium was fluctuated around zero and not exceeding 3 sigma 99 confidence level, 99% confidence level. This is the X-ray energy spectrum of round 1 during heavy water low mode electrolysis at the first week of the electrolysis. This spectrum lighting up in low energy region is regarded as somewhat similar to electromagnetic noise signals, but it might be soft breakthroughs of the nuclear brainstorm by child particles. The similar spectrum was observed at 1-2 during white water electrolysis. This result may suggest the possibility of the production of low energy, less than 200 keV charged particles, which generated no characteristic X-rays, but do brainstorm X-rays. At 1-6, the different X-ray spectrum was obtained at first week of constant mode electrolysis for the heavy water electrolysis using argent cathode, which was pre-processed by chemical etching. The MC data is shown in bottom figure, where we see X-ray event called as burst. The event might be no signals because no signals always appear as burst. This figure shows the NCS data at 1.5 during the constant mode heavy water electrolysis using annealed argent cathode. Only for the XL, which electrolyte was lithium-mode heavy water solution, neutron and X-ray includes the simultaneously around the time 17 hours. Much larger X-ray burst events after that event were probably no signals because there were two simultaneously burst events for the B cell, which electrolyte was lithium-OH light water solution. This is figure the expanded scale data for the neutron and X-ray coincident event. Because the time variation of neutron count rate is not identical to that of X-ray, the origin of this event will not be the same reaction if these events are signals of some nuclear reactions. But there is possibility that the triggering condition of two events will be the same solid state or chemical conditions of the purging cathode. Corresponding spectra of X-ray and neutron could not be identified because count in spectrum channels did not exceed statistical error level. Conclusion. In order to study the correlation between excess heat and nuclear product, the measurement of heat balance, X-rays, and neutron during heavy water or light water electrolysis using argent cathode were performed. In this part, the reliable twin system was used. Above all, the X-ray measurement system for the correlation study was improved. As a result, no excess heat beyond 3 sigma level was observed. But for only heavy water electrolysis using X-ray and neutron event occurs simultaneously. Other 3 X-ray events were observed out of 7 runs for both of heavy water electrolysis and light water electrolysis. And all of them occurred at the first week of the electrolysis. The energy spectra of X-ray were not characteristic X-rays, but looked like the brain strands. But these X-ray spectra were also similar to noise signals. We are now using high-resolution sequencer state detector cooled by PELT device to investigate these soft X-rays in lower energy in detail. In order to prove that these X-rays were not noise signals, but genuine soft X-ray signals, the simultaneous X-ray measurement by a bare detector and a detector covered with metal foil will be needed in future. Thank you.
The paper is open for discussion.
As far as I know, only cosmic muons accompanied by neutrons could produce a neutron signal and X-rays at the same time. Is it right?
As you are right, and the simultaneous debate we also possible F and B cell may come from cosmic.
Do you have any information about treating this type of experiments?
Richard, how is it?
Torsion, but not easy.
Sorry, we have moved on to the
Could you just tell us what the detection limit of your thermal measurements were? I see you use thermocouples for your temperature measurement. Could you tell us what you could resolve in terms of milliwatts or something in your thermal measurements?
Yes, the accuracy of the heat measurement is something like 4.4 watt of one standard deviation, which is 4.4. But the dynamic range is something like 50 watt. If
Any more questions?
The next contribution excess heat production. The title of the next contribution is excess heat production and nuclear ash in palladium oxide heterostructure after electrochemical saturation with deuterium by Dr. Lipson, Lyakov, Savov, Kuznetsov, Ivanov by Lipson.
I'd like to say about results of 6 years cycle of investigation that was trained on the determination of the nature of excess heat and nuclear ash generation in palladium-coal heterostructures, electrochemically saturated with hydrogen deuterium. In contrast to traditional for cold fusion experiments systems that are massive palladium samples saturated with deuterium. The system under consideration has some essential advantage in terms of obtaining of reproducible and controllable results. The first is short saturation time and absence incubation period that precedes to excess energy generation. The second is low current density in electrolysis process. Control of hydrogen or deuterium content in palladium sample at any time. Then higher reproducibility of excess in contrast to applied in electrolysis energy in each cycle saturation of palladium sample, and possibility of hydrogen deuterium concentration in a small volume on the palladium O interface. Experimental technique. Electrolysis was carried out in glass cell with subdivided cathodic and anodic spaces. The electrolysis used was 1 molarity potassium OH in H2O, and for deuteration 1 molarity natrium OD in dead power solution. Current density used of about 10 or 30 milliamperes per square centimeter. Samples was cold rolled palladium foils with thickness about 30 or 50 microns. The samples preparation was the next. The first annealing and vacuum at temperature 6 degrees of Celsius, 600 degrees of Celsius for 3 hours with slow cooling to room temperature. Then measured annealing in oxygen flame at temperature of about 1000 degrees of Celsius that leads to palladium or layer formation, having a thickness of about 200-500 angstroms. And then electrochemical deposition of gold on the one side of palladium molecule structure. Thickness of gold coating of about 2000 angstrom. For measurement, we use thermodesorption technique, gas thermometer. This gas thermometer diagram with neutron detector, and use a specially developed setup on the basis of electromagnetic displacement transducer with high sensitivity to determine in situ changes in the length of thin palladium samples in the dehydrogenation processes. For neutron registration, we use a block of 7 proportional neutron counters, boron fluor 3, placed into a tank containing vacuum oil and covered by cadmium sheet. To detect a gamma radiation upon thermal effect in the electrolysis period, we use semiconductor gamma detector, pure germanium, by EG and G or TEC, with efficiency about of 0.3%. On the electrolysis process, at the electrolysis time less than 40 minutes into the structure, the one-side bending of sample is observed. Like this. During electrolysis. This bending is cause of deuterium storage on the palladium ore interface. At the electrolysis time more than 40 minutes, the straightening of sample takes place due to deuterium breakdown into the sample pulp. The free energy or elastic deformation stored up in sample due to electrolysis may approximately be estimated with the formula. And the deflection, maximum deflection is about 5 millimeters. Then we obtain 76 calorie per square centimeters in comparison with the electrolysis energy applied is 7.8 calories per square centimeters. When electrolysis is interrupted pause with time less than 40 minutes, after the drying of sample, there takes place the thermal burst in air, atmosphere, or in oxygen atmosphere, which is accompanied by the heating of sample up to temperature of 900 degrees centigrade. This is thermal burst obtained from hydrogenated samples, and this is the thermal burst obtained for deuterated samples. If we use the structure without palladium or cohesion, after 2 hours of saturation, we have 0 thermal effect. The curve 1. The average energy of burst, of thermal burst, from 100 thermal burst is for hydrogen 15 calories per square centimeters, and for deuterium 20 calories per square centimeters. The reproducibility of these thermal flames is very high, and we obtain 1-200 thermal bursts in succession. That is statistics data, distribution of heat production events with respect to the heat evolution energy for hydrogenated system. We see that the average interval is 15 calories, while the energy applied in electrolysis over 2 times less. The magnitude of thermal effect can be increased Essentially, when specific surface of heterostructure sample will be strongly increased too. For this purpose, we use palladium black with particle size about of 1 micrometer, deposited by electrochemical method onto palladium core surface. At the same time of saturation, that was in this case, we have average energy in 100 flames in succession about of 35 calories per square centimeters, while the electrolysis energy is not changing. The reproducibility of this thermal burst at room temperature is equal to 100%. I must to say that the reproducibility of deuterium burst at room temperature is not 100%, but if we heating the samples about 40 degrees centigrade, we have the same result that in hydrogenated system. To determine the relation between thermal and nuclear processes in heterostructure, the simultaneous detection of excess heat production and nuclear radiation was carried out. The registration was began from the moment of sample drying and was finished at the moment of total gas desorption from sample. The experiments have shown no statistically noticeable emission of neutrons for hydrogenated samples. The distribution of the number of neutron ions with respect to the multiplicity of neutron pulses is well in accordance with the Poisson distribution. In the same way, the neutron emission from deuterated samples take place. It is neutron burst that we see when the samples are in the plastic deformation state after the contact with oxygen and near the beginning of desorption process. The distribution of neutrons, number of neutron ions with respect to the multiplicity of neutron pulses cannot be in accordance with Poisson distribution. The rate constant of DD reaction in deuterated heterostructure determined from this measurement is about 10 in minus 21 power per second per DD pair. The sample of this heterostructure were used for gamma measurements too. Here you can see gamma emission, this subtraction of gamma background from the deuterated heterostructure. Here we can to find three fields in which we see any excess in gamma gamas. It is the narrow line with energy 2.225, broad lines 3.8 and 6.3 megaelectron volts. The narrow line with half width of about 10 Hz could be ascribed to P plus N reaction because its position is in a good agreement with the gamma lines from thermal neutron capture and polyhydration result. In contrast to deuterated heterostructure, the samples of hydrogenated structure has only one line. There's only one line with position of about 406 megaelectron volts. Under neutron irradiation, this line increased more than 5 times and shifted on 0.3 megaelectron volts. Therefore, excess energy generation in our palladium DH heterostructure is accompanied by gamma emission. The gamma emission intensity depends upon the thermal neutron background. Moreover, I can say that, as it's shown by Dr. Rusevsky, desorption processes in heterostructure that was produced in our institute, both H and D saturated, is accompanied by emission of charged particles, protons, and possibly alpha particles with intensity of protons about of 0.8 protons in 40 envelope. In conclusion, thermal we see in heterostructure of this type, deuterated heterostructure and hydrogenated heterostructure, the anomalous thermal effect with value about 2 or 5 times more than the electrolysis energy applied. We see a neutron emission only for palladium OD samples with intensity. We see the burst of this emission sometimes with intensity of 100, 500 newtons per second per square centimeters. We see gamma emission for structures of post time with this energy position fixed. In conclusion, I can say that simultaneous generation of excess energy and weak nuclear radiation in heterostructure, as well as strong plastic deformation in it, I indicate on the possibility of unknown laser action in system of this type. In fact, the main processes that determine heterostructure properties in the after electrolysis time is an intensive exothermic desorption of hydrogen from the sample. This effect from other side is main condition to unknown laser operation in palladium-palladium O interface in the high loading ratio zone, where the clusters of hydrogen are alkalized. As a result, both excess heat and weak nuclear radiation are absorbed in this connection. In this connection, the short electrolysis process for heterostructure saturation with hydrogen on deuterium can be considered as pumping up procedure of unknown mass. Moreover, results obtained on excess energy yield in this type heterostructure in electrolysis period with yield about 130 or 300% from energy applied are background to our research group to design environment power device with output power of about 1 kilowatt per gram per hour.
Okay, thank you.
Thank you.
If I may comment on the first two parts of your talk, the thermal flash that you claim you observed is very similar to the cigarette lighter effect that was well known to operate last century, where you just take a palladium rod, fill it with hydrogen, contain it, and when you want to light your cigarette, you open the top, and you expose the top of that. Some of the hydrogen escapes. By escaping that warmth of palladium, it acts as a catalyst, and it gives you this thermal flash, which is a very well-known phenomenon. I could not understand the calorimeter to get the amount of energy you're doing. I mean, if I were to...
Can you speak slowly, please?
I'm sorry.
On the point,
The first thing is your thermal flash is the well-known cigarette lighter effect, which before matches were invented was used last century. The calorimetry I could not understand. If I were doing it, I would make 3 concentric chambers. The inner one is where you drop your palladium rod, or you put a heater on which you give a corresponding pulse of energy and time. And then the 2 outer ones are filled with water, which temperature you measure, and then you determine this. But I don't know whether that's how you did it. The second comment is about your neutron bursts. Now, we have already gone through neutron bursts with Steve Jones and Howard Menlo. And what they did was they had a series of neutron detectors, and the neutron detectors were all linked together. And they found bursts with many neutrons. But then they segmented the neutron detectors, and therefore they said, if
I know.
And you know, okay, so I mean, you should get separate segment. Do you have segmented neutron detectors?
No, we have not segmented neutron detectors, but we have a large statistics. We have statistics of background, and we have many these statistics, and we know that in the time gate of 1 microsecond, we cannot see the events with multiplicity more than 3 in comparison with our results where we have multiplicity 80. For our 6 years measurements for neutron background, monitoring of neutron background in our place, we have not seen this multiplicity.
Would it not be useful to learn from the experience of Steve Jones and
And we have control experiments with heterogeneous structure where we cannot to obtain those results.
Okay, one comment or question. So, please.
I understood that you believe the elastic energy represented by the curved specimen was somehow useful in producing nuclear reaction, yes? However, that curved specimen does not have elastic energy in it. It only has plastic deformation, because that's a permanent curvature, is that correct? That it's not like a spring, you let it go off back again. That represents the stored energy of dislocations. That's a very, very small amount of energy.
On the first stage, it is the store of the energy of dislocation, but after electrolysis time, when we put our sample and dry it and contact it with oxygen, the strong exothermic desorption take place.
Combustion.
And there we see anomalous thermal effect and nucleation.
Well, my only comment, other than I think you have combustion, just as Douglas says, my only comment is that you do not have elastic energy to do anything useful. You always have this dislocations that are stored in the mineral, and that's a very small amount of energy.
Okay, you know, time is completely over. So thank you again.
Next paper is a dynamic movement of hydrogen isotopes. So the presentation is combined with paper 41 and 42. And the first one is dynamic movement of hydrogen isotopes in pulse mode electrolysis by Ogawa, Oya, Aruga, Ono, Aida, Okamoto. And the second paper is correlation of excess heat and neutron emission in PDLI electrolysis by practically the same authors from a research laboratory for nuclear reactors of Tokyo Institute of Technology. The papers are presented by Dr. Okamoto. Please.
Thank you, Mr. Chairman. I want to close this conference just on time, so I save a minute to good schedules. So the first, I want to show some new result titled Dynamic Movement of Hydrogen Isotopes in Pulse Mode Electrolysis. These two studies have been supported by a basic research project of new hydrogen energy, financially supporting 20 Japanese industries. Almost of my presentation has been displayed on the poster board, the second poster session. So I skipped some details there. We have a nice empirical equation to estimate the excess heat introduced by Makoeto group. So we have a very interesting point. First is some threshold of 200 milliampere per square centimeters, and also this term of dx over dt. It means the dynamic movement of the deuterium or hydrogen in palladium cathode. So at first presentation, I will show some very interesting data to you. This is a test palladium cathode. This is the same size of our mainly used in our energy research. This and the D over PD value of the D over PD is recognized by us as a very good sensors for the movement of the hydrogen isotopes in cathode. So we have some uncertainty or discussions on the D over PD absolute value by what method you used. So this is very good technique to monitor the D over PDs quantitatively. This is a apparatus system for measuring the dynamic movement, change of the D over PD ratio, it's very simple. And others, electrolyte solution or concentration, and it's the same as what we were used in our excess heat measurement system. And also, we used these relations to estimate the D over PD ratios from the resistance change. This is the typical basic data for checking the loading rate, not loading ratio, loading rate at the start of the electrolysis with constant current. So this shows for hydrogen isotopes case, we have some high loading rate from this first part of the curves. We have some little isotope effect between hydrogen and heavy hydrogens. This obtained for heavy water electrolysis. There are some different shape of the constant current electrolysis and after the cut of the electrolysis. And when we change electric current density, we obtain this data from the same conditions experiment. The smallest electric current density is 40 milliamperes per square centimeter, and the highest 800 milliamperes per square centimeters. This highest current density has been used for our main NHE studies. We calculate the loading rate from the first step of the loading curve and estimated this, obtained this value, and plotted versus to the current density. From this 6 point is obtained from the very thin electrode, so this is some kind of difference between this. But at around 200 millimeters per milliampere square centimeter current density, the loading rate is kept constant. So we now considering this point is very important point as suggested by the SRI equations. But unfortunately, my brain not so good, so I even now cannot find the physical meanings. So, on the dynamic movement of hydrogen isotopes in tritium cathode was traced according to our high-low mode, pulse mode electrolysis, which was found by Professor Takahashi. So, from this, when the same electric current density mode, repetition time was 1 hour, we cannot find any dynamic movement. But the repetition time became longer as 3 hours we can see these blue lines, the dynamic movement of the loading ratios. I mean, this is a good trace of the dynamic movement of isotopes, hydrogen isotopes in cathode. Okay? And this 3-hour reputation time is a very, very important factor we found now. And 6 hours, and this is the red lines, also gave us very appreciable dynamic movement. And this is first findings. And the second, this graph shows we have a very anomalous isotope effect occurred in the same mode of electrolysis between hydrogen and deuterium. This red curve came from this experiment for deuterium, and the same conditions for 440 to 400 milliamp per square centimeter electrolysis. In the case of hydrogen, we cannot see so appreciable dynamic movement. It's evidently from this curve. And also, this loading ratios change tendency is just opposite between the hydrogen and deuterium. This is new findings, and it's very interesting for me, but at this point also find no explanations. I would like to say some conclusions. The dynamic movement of hydrogen and deuterium cannot be observed in the first models with the current density lower than 200 milliamp per square centimeter. This is very important factors or values. And the dynamic movement of hydrogen isotope cannot be observed in the Earth with 1 hour reputation pass. The dynamic movement of deuterium with clear responsibility to the high-low electric current density can be observed in the highest current density, higher current density larger than 400 milliamp pairs per square centimeter. And longer reputation time, 3 hours. While the responsibility of hydrogen is very slight. The loading ratio of deuterium increase in the high current density and decrease in the low current density, while the loading ratio of hydrogen does in just reversal move. Okay, so the pulse modes, the number 7 conclusion. The pulse modes applied in the NHE studies by the present authors. High current density is 800 milliamp per square centimeter, and low current density is 20 milliamperes per square centimeter, and replication time is 3 hours over 3 hours. Seems to be reasonable to generate excess heat and excess neutrons from palladium LiOD platinum electrolysis method. So I want to go ahead the next presentation. Correlation of excess heat and neutron emission in PD energy electrolysis. According to the conclusions of the previous last studies, we carried out one series of electrolysis with the same conditions. And to avoid the uncertainty or unclear point or discussion point to the excess neutrons, comparing with the light water system and hydrogen heavy water systems. And so we set up the same two experimental systems. So we can carry out the background experiment and foreground experiment. Background means electrolysis with light water, and foreground means heavy water electrolysis. In the same time, in the same period, in one experimental room. This is the assembled experimental system. So it's very easy to find details. We have two same designed measuring system, and we made a neutron energy spectrum. We obtained a neutron energy spectrum with 8 inches and 2 inches very big energy 2/13 liquid scintillation system, and we have some excess heat monitoring system. This is the view of our systems. Every message written in Japanese, so it's very good secret word for you, but I have no secrets. We have many Chinese friends here, so please translate to English. Yes, I should say again, our experiment carried out at the same time with light water system and with heavy water system. Okay, this is very, very important. So, as I said to you before, my brain is not so clever, so we want to find some difference between comparison with light water system and heavy water system every time. Okay. I want to call this everything came from the hydrogen isotope effect in our experiment. This is the total system of calorimeters. The detailed view of our cell is this. We have palladium cathode, plate cathode, and platinum wire anode, and 3 resistance thermometer for control and for check the thermal balance of this calorimetry excess heat monitoring system. And when one of these was broken, whenever broken, we can obtain some data. And others are very, as same as we reported before. And today, we put the level adjustment system to keep the electrolyte level or volume to be kept constant. Okay? This is also very important. And so this droplet, putting new electrolyte is very, very small amount or volume. So that this dropping has not any kind of influence to measuring the temperature of electrolyte. This electrolyte around 700 milliliters big. So it is also very important point to estimate some excess heat. あと何分ですか？10分前にしたらシグナルつきます。トータル。ありがとうございます。This is the experimental conditions. As I said before, we carry out the experiment every time, always to these couple, background and foreground, background, foreground. And the same palladium cathode were used. And pre-treatment of this cathode just described in this column. And high-low mode, as I said, 800 to 220 milliamperes per square centimeter, and repeatation time is 3 hours. And before the beginning of the experiment operation, we check the functions of two sets. Here we can see this curve is just for clarity. This is a calibration curve of this set for background and foreground. Over the minimized input energy, these two curves is no change before the electrolysis and after the electrolysis, and also this hydrogen system, heavy water system, almost same the calibration curve we can get. And also for neutron, excess neutron measurement estimation, we check the 213 system. Of course, in general, there are some difference for the detection coefficient or something else. So we, for 1 month, we count background with light water and heavy water and some set of the electrode rods, but no electric current. Okay, no electricity, but every material is just set. And for 1 month, and after the obtain the neutrons count rate, we set up some correction factor. After using the correction with such a factor, the foreground, background, neutron counting rate ratio is just on the unit. These errors become bigger and bigger, came from the higher energy neutrons count rate become very small, very small. So the errors should be large. Okay? And the first one, the temperatures was measured for these two systems, background and foreground. This experiment carried out in November of last year. we have very big isotope effect, even in such a electrolyte temperature change. So this from the shift of the temperature measured point from the temperature curve, we estimate some excess heat. This is the result of the obtained excess heat, and we show in this graph with some histogram. This is foreground, and this is background. In the light water case, this distribution histograms is just distribute the same sign, and excess heat was distributed like this. It's very clear, excess heat, I say. And at that experiment, we found some excess neutron shown in this view graph. The low energy part, we can find some excess neutron. This is the background polarizations. Okay? And this is also very important and interesting data. We measure cell voltage. It means that cell voltage in the operation of electrolysis. We can get these graphs. This curve, please make your mind, is changed from like here to the debris rate is increased and not linear. I mean, it is not linear. Number two, this is we cannot find any excess heat. In such a case, the old temperature point is just on the temperature bar. So the same histogram also indicates that we have no excess heat, something like this, okay? And in such a case, no new hydrogen phenomena was found. The cell voltage and electrolyte temperature increase gradually, like just linear functions. The third recent data is this. In this case, we continued 6 weeks operations. So clearly from this graph, these temperature points appreciably shifted over the calculation. While the background case, all of the points is just on the calculation curve. And the same treatment showing you like this. So upper graph, the horizontal axis is excess power, and lower graphs, horizontal axis is the excess power percentage for to the input powers. Both these histogram also very clearly indicate we have some excess energy. And finally, I want to show you the very, very fantastic result between the, we have some time correlations between the excess heat generation and excess neutron emission. This is the first 1 week, second week, and 6 weeks. So excess heat is, this is a histogram, clearly increase, and along with this increasement of excess heat, the neutron ratio, which means excess neutron, is also increased, something like this. Okay? And also the same meanings is easily found from this view graph. And how is the cell voltage change in this case? We could get this data from the number 3. Lower 2 curve came from for background electricity, light water electricity. While the heavy water electricity gave us this very enormous, mysterious change of the cell voltage and just same tendency on the electrolyte temperature. This part is not so different from the previous 2 data, but this non-linear part is very, very fantastic. But this is not possible. This was presented in a Mallove conference, I know, maybe so. In this one, we could find very appreciable excess heat. And also in this case, we have such a nonlinear increase of cell voltage. Maybe the cell voltage change caused by the change of the palladium cathode, I think. But, sorry, I have no idea to explain now, so I go ahead to conclusion. The coincidental expander system worked well with adequate stability for the variation of the excess neutron and excess heat without the uncertainty caused from the different experimental data. The excess heat generation and the excess neutron emission could be replicated and the same electricity condition of the pulse mode operation. The time correlation between the excess heat generation and the excess neutron emission were observed clearly. It is the first data in MHE researches. The anomalous isotope effect was found in the apparent cell voltage. The nonlinear cell voltage increase has a time correlation with the excess heat generation and also with the excess neutron emissions. Further investigation should be carried out to complete the replicability of the excess heat generation and the excess neutron emission, and to optimize the cell system to generate larger excess heat and to intensify the evidences of the nuclear phenomenon, and to elucidate that anomalous isotope effect occurred in the cell voltage change. Thank you very much.
Question? I cannot agree very well that there is, in your case, a significant statistical neutron signal. If you account for statistical error and systematic error, I suppose your result is not very significant. Have you controlled the temperature of the NE213 between the first week and the 6th week? There are 6 weeks between your negative neutron, according to you, the effect and your positive neutron effect. Can you show again the picture with 6 weeks?
I show you. And the room temperature was very well controlled for through the years, and also the humidity is controlled perfect. I would say to you. Okay.
The first week was in spring and the 6th week was in summer, right? Well, if you put some systematic errors in those pictures, can you say what's the level of systematic errors?
No. Sorry, I have evidence to reply to you now, but we have many statistics data also. I will show you.
I wouldn't worry much about statistics. I would think we have an interesting correlation. It is somehow reproducible compared to all the other negative things we know from before. But the question is this perhaps due to a phase transition in the material? Because it would be not a point of excitement now if very small numbers of nuclear reactions are produced in materials by a phase transition. Whether it's crystals or anorganic materials, compounds, or metals or whatever. Now, can you exclude phase transition? This is my question.
Of course, we should consider such a phase transition. Our experiment, of course. But impurities severely controlled in our system. So the first round and the third round is very different data we show you now. That we have a very serious, significant difference in impurity control.
Okay, thank you. Second question, you mentioned something about isotope shift.
Yeah.
Can you elaborate this a little bit more again?
Yeah.
What was it about isotope shift situation?
Well, the isotope shift. For example, this one?
Yeah.
This is general isotope.
motion, so-called.
I think this is bearing on my question. When in your comments about you were using light water as well as heavy water, right? I mean, you weren't the languages. There was a question about the language. It was not clear when you said that you had, or I'd like some clarification for myself. You talked about a nonlinear cell voltage effect, and you talked about anomalous excess heat for light water. Is that correct?
Yeah, maybe.
That is correct. No, it's not. No, all right. So you didn't. Did you ever see? You never did light water.
Never.
Never. Okay.
Never.
All right. Fine.
May I see the other slide, the one you showed before, with the 6 weeks again, please.
6 weeks. This one?
Yeah. Your explanation was not clear to me. The meaning of the points in the neutron signal which are under the 1. I mean, you have point between 0.9 and 1. What is the meaning of this point? It's not clear to me.
Point 1.
You have experimental data between 0.9 and 1.
sometimes, yeah.
Yeah,
Because,
what's the meaning of that point?
because these statistics are very wide. Because the counting rate is very, very small compared with low energy areas. Okay, I have some data on this point. This is 1 week's total count of bunch fast to 4. This is low energy part. The counting rate is very big, but the highness decreases so it is. This is not so. Okay. Another
Last question.
In your experiment or from your measurement, can you estimate from your result about the neutron emission? Can you estimate the reaction rate?
No.
By considering the detection efficiency or something?
Yeah. We can.
It's very important thing.
Yes, we can. But this evidence intensity is not enough for me to calculate such a concentration. Yeah, thank you.
Very short question.
I would like to explore the calorimetry aspect. 2.5% deviation from zero for excess power is not very large, so I need to ask, what is the reproducibility of your calibration? What are the mean, the standard deviation of any one calibration, and how does one calibration today compare to one tomorrow or the next week?
Yes, we can check every day, of course, but according to our experience, for weeks long, just before the electrolysis, we make a calibration count and check after the electrolysis. They're almost the same.
What is the standard deviation of your calibration points from the reading?
The same temperatures should be kept to 24 centigrade degrees C, plus minus 0.01, and bigger deviations is 3 times or 4 times up. So please calculate.
Thank you very much. Okay, final paper. This afternoon. The title is Excess Heat Measurement in Gas Loading Deuterium Paradigm System. Represented by Dr. Lee, Ye, Han, Si, Ga, Lee, at the Tsinghua University, and also Beijing General Research Institute. So, Professor Lee, please.
Thanks, Chairman. My talk is about excess heat measurement in gas loading system. Gas loading means there is no heavy water, no light water, just 2 bottles, one filled with deuterium gas, one filled with hydrogen gas, and we watch their behavior and extract information for excess heat. We put a thin, long palladium wire in a bottle, wind on a quartz frame. Put them into a vacuum Dewar system. A platinum thermometer used to measure the temperature. The tungsten wire is essential for the high loading on the palladium wire at the pressure less than 1 here and maintain for several months. This dual system is made of stainless steel thin wall. So the heat conduction plays the dominant role for heat transfer instead of heat radiation. Let's look at his calorimetry feature. This is the temperature difference in logarithm. If we heat this system at a constant power, the temperature is constant. Then we shut off the heating power in the tungsten wire, then it drops like a straight line based on the Newton's heat conduction law. Then we turn on the heating power again, it increases the temperature. But if we control the heating power, it flat again. Compare these two numbers, 1.9 watts and 2.1 watts. We know this system can distinguish 0.2 watts. So we are sure we can measure the excess heat at the level of 1 watt per cubic centimeter palladium. If we turn off the power again, then it starts cooling. This is supposed to be a straight line, but important is this temperature. If we use the temperature half degree higher, it bends up. If half degree less, then it bends down. So use the straightness, we can measure this temperature with high accuracy. This temperature is very important because we put them together. There is excess heat information in this temperature. We call it theta F. So there are two ways to measure this temperature. One way is the heating method. When you heat it at a constant level, you can get this temperature. The other way is using cooling method. When the temperature is going down, you can use this straightness to figure out what's this number. Finally, if we do not heat it and cooling to the end, when the room temperature is cycling day and night, we still can extract the information for this excess heat, which is proportional to the temperature derivative, but with negative sign. So first, we worry about whether they are real twin systems. They should be same in calorimetric feature. There are two lines. This is the time. This is the temperature difference in logarithm. The blue line is for the deuterium border. The green line is for the hydrogen border. If every point is on this straight line, this correlation coefficient should be 1.0. So we are sure it follows Newton's conduction law. And we are sure the difference between this slope and this slope is very small. For deuterium, it's 4.18. For the hydrogen border, it's 4.23. So we are sure they are real twin, but they are different in the theta x. When we draw this straight line, for the hydrogen border, this number is 30.85. For the deuterium border, it's always higher. For this case, it's 0.84. At first, we worry about calibration. Maybe we have some systematic errors. Now, we can change this number. If we heat by the tungsten wire, then we will see this number will be controlled. is the time, this is the temperature, not in logarithm. This straight line is the room temperature. In the hydrogen model, when we heat it, temperature increase, then approach a constant number CIF. For the deuterium model, we heat it, it approach another temperature. This temperature is always a little bit higher than this. And we change this heating power, it will go to different final temperature. So we can calculate the temperature difference between this number to the room temperature number. Then we list them in the following table.